Alright, so anyway, we represent our object by a box, and we put a dot on the box to represent the anchor point for all of our vectors. And just to back up a little bit, we remember that if you have an object on a horizontal plane, there are a number of vectors that have to exist. What's one of the vectors that has to exist? Gravity. So how do we represent gravity?
FG.
FG with a downward arrow,
Yeah.
so FG. And if it's not falling through the plane or accelerating off the plane, then there also must be a what? Fn. And how does the Fn compare to the FG? Same, yeah. Same magnitude, opposite direction, F sub n. Okay. So far, so good? Now, when you were pulling, when you were pulling the friction block, it was very important that you pulled it at a constant velocity. Why? Why was it very important that you pulled the block at a constant velocity?
Was it like a control factor?
Oh yes, it's very important. So constant V necessarily means what?
I mean, because you have then have a constant friction.
You can actually change the friction with the velocity, but stepping back, we're jumping over a few steps. What does a constant velocity necessarily mean?
Zero acceleration.
Exactly. So constant velocity necessarily means that acceleration is zero. And if acceleration is zero, what does that necessarily mean? It's true, but the forces are...
So it's only kinetic friction, right? Instead of like no static.
In this case, yes, we're overcoming kinetic friction. But when you have a constant velocity, that necessarily means, hey, Scott's here. That necessarily means your acceleration is zero. And if acceleration is zero, that necessarily means what? The forces are in equilibrium, exactly. That means
I was going to say that, but
F net in x and y is zero. Okay? The forces are in equilibrium. Okay? We call this situation equilibrium when you have forces in the x direction and the y direction that cancel out or are in equilibrium. They are the same magnitude. Now, why is this important? Because what two forces were we looking at in the friction blocks lab? Okay, so we got normal force in F and G, then we were dragging it, and
for friction.
force of friction.
And then is it F of, what is the force? Is it just F? Like force?
Just F of FA, so applied force. And
What is the A?
if, this is very important guys, if you were moving at a constant velocity, which necessarily means acceleration was zero, which necessarily means net forces were zero, how does the friction force compare to the force applied? They are equal.
When they're moving?
When they're moving. So if you are moving horizontally with a constant velocity, that necessarily means acceleration was zero. So if acceleration was zero, that means the net force was zero. So that means net force was
Because
zero.
The friction force was less.
That
it'd
means
be
force of
accelerating.
friction is
If
force
friction force
applied.
was more, it'd be de-accelerating or slowing down.
Right.
However
Okay.
you want.
So remember, friction force can never be larger than force applied, because that would be weird. The friction force can't cause motion in the opposite direction.
Well, wouldn't it be slowing it down until it hits like static?
Yes. Yeah. It would actually create a negative acceleration. Yeah, you're right. So if friction force is larger than acceleration, force applied, there would be a negative acceleration. But in our situation, we have net force is zero, so force of friction this way equals force applied that way, which means the friction force that was on your scale, which was force applied, was also equal to what? Force of friction. Okay? So that thing, whatever the little spring scale said, is your force of friction. Does this idea make sense? Okay. That's level 1. If you are ready to move on to level 2, give me a thumbs up. If you want to talk about level 1 again, wave your hand around. Okay. Sure. So, from the top, it was important to move the friction block at a constant velocity. And the reason it was important to move at a constant velocity is that meant acceleration was 0. And if acceleration was 0, then the net force in that direction was also 0. Much like your downward weight and your upper normal force are 0. That way we know that is the case because you're not flying off your chair or falling through your chair. So, and if the net force is 0, that means all the forces are in equilibrium, so the force of friction pulling back is equal to the force applied pulling forward. So you look down, you see your spring scale, that's the force applied, that's also the friction force. Yes?
Is this on a flat plane or an incline?
Horizontal plane so far.
Oh, the force.
Yes?
Okay, so even though even though it's being pulled, freaking force you're still in equilibrium?
As long as we're moving at a constant velocity, we are at equilibrium. So,
Well, yeah, I was kind of thinking the same thing, like, if f of g and f of n they're equal, and so it's not moving up or down. But if f of f and f of a are equal, then why is it moving?
because we need to separate velocity from acceleration. So the concern is, it is moving, we're saying it's not moving when there's no net force, but it can move, it just can't accelerate. So much like you and I are currently moving at several thousand miles per hour
Fun.
with respect to the center of the Earth.
Fun.
Yeah, we're moving really fast with respect to the center of the Earth. We're not accelerating in the horizontal direction with respect to the center of the Earth because we're pretty much planted right here. Down there is the center of the Earth.
Would we all
Oh,
get dizzy
so
if the
wonderful.
Earth stopped
Yeah.
spinning?
If we ever stop spinning, you'd experience a tremendous acceleration as your inertia would basically, you'd start to slide. But basically everything would start to slide with inertia and the Earth would stop moving. So it would be like the Earth would moving, the floor would be moving in the opposite direction of you. The building would fall in. Anyway, so that's what's important. So with a net force of 0, you have to have an acceleration that equals 0, which means your forces cancel out.
I have a question regarding the whole Earth stopping moving.
Uh-oh, I was afraid of that.
So say you're in a plane or you're falling, like you're skydiving. How would it work then?
If you were skydiving when the Earth stops moving, you would start moving horizontally.
Okay. What
Because
if
you would be like, hey, the buildings are moving away from me.
Oh, would that be because so
You'd probably only see a cloud of dust though, because the buildings would obliterate each other. You'd basically be landing in a cloud of semi-molten dust. Tremendous friction would basically cause the entire surface of the Earth to catch fire and melt.
Oh.
You'd live a little bit longer than everybody else because you'd just be encountering massive wind. So you would be carried along with this giant hurricane as you fell.
that'd be fun.
Yeah,
That's
not a bad way to die. Anyway, so moving on.
That's crazy.
So if we're okay with level 1, give me a thumbs up.
Yeah, I'm good with level 1.
If you're ready to move on to level 2, give me a thumbs up. It's like about half of you. Anyone have any questions about level 1? All right, so now we're going to take this plane and we're going to lift it at an angle theta. Why theta? Because it's always theta. First angle is always theta, second angle is always phi. This is the way it works. By the way, this is theta and that's phi.
What's
First angle, second angle.
oh. Just wait on that.
Anyway, so let's look at the vectors that are present on our inclined plane. So glad you are all here today. We're recording it, this is important. All right, so what's one of the vectors that's going to exist on this object on an inclined plane? I have an inclined plane, by the way, it's right here. I'm not going to lift it up because the number is going to change and it's going to reveal the punchline. But it's right down there. Okay, so what vector must exist on our block? Gravity. Okay. What direction is gravity?
Down.
Straight down. Right, gravity is straight down.
Is it normal force?
F, G. What else is there?
Normal force.
There's a normal force. We know there's a normal force because what is the block not doing to the plane?
Going through it.
It's not going through it, it's not flying off of it, so there must be a normal force. And we'll just make the normal force green. That's why. Do you understand why I drew it that way? And not opposing gravity?
Is it because how it's angled?
Normals are always perpendicular to a plane. That's kind of what normal means in science. It kind of means perpendicular to a plane. Like, well, I'm gonna run normal to the sidelines. That's not gonna get you anywhere. You're gonna be running around one line of scrimmage. If you run normal to the line of scrimmage, then you're going straight vertical to the end zone. Okay, normal basically means perpendicular to a plane. Okay, so what other vector must exist?
Force applied.
Force applied, which we're going to do last. Very good, though. We're going to talk about that.
Friction force?
Friction force, okay. So there's going to be a friction force, which is going to go what direction? If I have my textbook, or have my textbook. If I have my textbook, the coin situation is a textbook, a coin on a textbook. So here's my textbook. I'll just place it right on top of the calculators. Boom, all right? And I get my coin. The coin will be represented by a 62th gear. Boom, all right. So now I'm gonna give it an angle. What is keeping the gear from sliding down the textbook? The friction. What direction is friction acting? Up the plane.
You understand.
It's going up the plane, friction force. Okay, now looking at these forces, something's kind of odd here. And something's kind of odd in that there's a force missing. Because if I have it like this and force of friction is acting up the plane, what direction, based on that diagram, what should the gear be doing? It should go up the plane. So there's a force that's acting against friction force. What is it?
Gravity.
We'll write that in there though. So friction force still equals mu Fn. And it's going to keep it equaling mu Fn forever. And friction force is always going to be perpendicular to normal force. So, but what force must exist? You can name it if you want.
Acceleration.
Let's not call it force acceleration.
Kitty, what'd you say?
What caused that to accelerate? What direction did that thing accelerate? It accelerated the direction of the cover. We might say it is accelerating parallel to the plane. Yeah. So it's accelerating parallel to the plane. I'm all out of color, so I guess I'll have to use black. Okay. So it's accelerating parallel to the plane. Force parallel. So if we zoomed in on this, we'd see force parallel going this way. We'd see friction force going this way. We would see gravity going this way. And we would see normal force going that way. The inclined plane, everybody. There's a more exotic inclined plane which you can learn later on, which we used to do in Physics AP, we don't do it anymore. It's about when a car goes around the surface. When a car goes, like a race car goes up and hits a banked plane. There's the banked plane versus the inclined plane. But we're not gonna do that anymore. So if you happen to be doing a little extra tutorials for yourself online, you care about the basic inclined plane, not the banked plane.
Doesn't the banked one also use like inertia?
No.
Because like
It still uses friction, but the math changes a little bit. Because the friction becomes a bigger, the friction becomes a more complicated term. All right, so these are our four forces we care about. Now, listen carefully. If gravity were not there, would the gear slide down the book? If there were no gravity, would the gear slide down the book? No. So that tells us that the force parallel must have something to do with the force gravity. Make sense? Yeah. And if there were no gravity, would the book need to push against the gear? So what else has to do with gravity? Force normal. This also tells us that force normal is also having something to do with gravity. Okay? So there's a missing term here and a missing term here, which we're going to write in. Thumbs up if you're good with this. Wave your hand around if you want to talk about that again. All right. Yeah. Yes. Okay. So we know that the gear is going to slide down the plane because gravity's there. We also know the force normal has to exist when gravity exists. The two, yeah.
Okay.
Okay, so this equals this plus multiplied by some term. Force normal equals gravity multiplied by some term. Now, if the plane is horizontal, then the normal force pushing up on the block equals the gravity. Yeah? That's what we talked about? So if we look at the angle, it's going to have something to do with the angle. If we look at the angle, is there some trigonometric function where angle is 0 makes this 1, and angle is 90 makes it 0? Because what's the normal force at 90 degrees? 0. So is there some trig function where angle is 0 becomes 1, angle of 90 becomes 0? Cosine. Yeah, cosine. So, cosine. So Fn is Fg cosine theta. At a very small theta, the Fn is pretty close to gravity. Okay, pretty close to Fg. Now on the other hand, the force parallel also has a function of theta and Fg. And most of you just like, by process of elimination, is there a trig function where force parallel equals gravity when the angle is 90, but when the angle is 0, it's gone? So when the angle is 0, is there a trig function that's 0 and angle of 90 becomes 1? Sine. So here is our new functions for our inclined plane. Force parallel is Fg sine theta. Force normal is Fg cosine theta. I need a volunteer. Someone with good balance. Aiden, no.
I actually have great balance now.
Oh, okay.
No longer
Aiden's got
have
great balance now. All right, then come on up.
Oh shoot, his thing's off.
This is the part where fires hits a hernia. Okay. So this is what I need you to do. Remember the force plate? So stand on the force plate. Put your feet together. Normal. Stand on the force plate. All right. There's Aiden's weight. Aiden's weight is 465. Now I'm going to do something kind of interesting.
400.
Assuming I can, and I don't throw my back out, I'm going to lift the end of the board. The board is 3/4 inch plywood. It's pretty tough. I'm going to grab the end of it and I'm going to lift it slowly. So realize that you're going to be tipping a little bit. Feel free to adjust.
Can you do it?
Are you going to? No. You volunteered, you're stuck. Okay, so here we go.
No, I mean like you want Kate to lift the
I
board.
feel like we should watch this
I'll give it a
to
try.
see if Mr. Byers is
Ready?
record it.
Here we go.
What's your leg?
What's happening to his force?
It's down.
It's going down ever so slightly.
Okay. Yeah. Go pitch down again. So, want to see it again? Want to see it again with the line? Here we go. Okay, then down again.
Just because it's by value,
Yeah.
so it's hard to see.
And auto scale. There he goes. Okay, so thank you. So what happened to the force? The force went down as the angle went up. So what is it measuring? Which one of these vectors is the force plate measuring? Normal force. Yeah, it's measuring normal force. So it's measuring normal force, and as the angle goes up, the normal force goes down as a proof. And in fact, I can basically put Aiden on the board, put a couple textbooks under it, and say, I know what that angle is. Could you do that? Is this something you could do?
Enough practice.
What if- No more forces agreeing. What if the scale measure was it 700? Yeah, 730. So what if the scale measured 730 newtons, and we know that Aiden's weight to be 770? 770 newtons. Could you figure out what the angle is? Could you figure out what that angle was? Where the scale said 730 even though he weighs 770?
Found that angle.
Yeah. Could you find that angle? How might you do that? What formula might you use to find that angle? The bottom one, yeah. So we would say, all right, so Fn read at 730 newtons, and we know that he's actually 770 newtons, cosine theta. So you can solve for theta. You can say, all right, theta must be the inverse cosine of what over what?
730 over 770.
730 over 770. So go ahead and do that. And then once you get a number, show your neighbor and say, see, I'm paying attention and working, and you're not, because you don't even have a calculator. Anybody need a calculation device?
I do. See, you're not a worker.
I did.
You're not a worker.
Ah, my eye. You threw a calculator at me.
What?
Is it 18.5?
Wait till you grab it.
Chemistry will be reading quantum physics for babies next class.
Why don't we?
You read it last year.
But we all read it. You saw it.
Okay. No, we're reading chemistry if we do quantum. You can do quantum in the spring or before.
So like, what is quantum involved? Like,
Electrons and how they move through the atom.
oh, so it's that's
how they attain energy states and
so there's
such.
that's okay.
Quantum mechanics.
I think my high school
Melissa
said
that she wants about you.
Okay. So bang on those calculator keys and we'll see if we can come up with an angle.
I got it. I got
18.5?
I did get that angle.
Can I just round up to 19?
What?